Okay, next section here in Bayesian stats is called Bayes' theorem. Statistics, we defined it earlier. It's a fairly broad term. It encompasses measuring things, collecting data, being able to visualize, make some predictions here and there too. It's a pretty broad category compared to some of the areas of math that we've looked at, which are extremely tightly defined. The other thing is that statistics is a relatively new area of math. Before the late part of the 19th century, really before the 20th century, most of what people meant when they were talking about statistics, it was just gathering measurements. It was like vital statistics. And so the kind of statistics that I use, or my peers use doing predictive modeling, most of that comes from the 20th century. And most of that emerged right alongside things like cybernetics and lambda calculus and all these other new things that we've been talking about in terms of machine learning. And I really want to underscore that point that the stats that I use is really from more of the computer era, if you will. But oddly enough, there's a big branch of statistics. We talked about frequentists a little bit ago. That came out of the 19th century. And in an odd way, it prevailed for a long time over an earlier concept, which was arguably much more robust, but less accepted, an earlier concept that had come out of the 18th century. And that kind of dominance of frequentist notions, it really held until we got to big data. And then we realized, actually there's a problem here. Thomas Bayes was a mathematician and I believe a Presbyterian minister in Britain during the 1700s. And he was elected as a fellow into the Royal Society in 1742. People were attacking the credibility of Isaac Newton and the math that he'd worked out. And so Thomas Bayes got elected as a fellow for defending Newton. So good stuff, good stuff. He also had written a paper postulating or presenting a set of postulates about conditional probability. And he'd written this shortly before his death. It was published afterwards. Somebody had published the letters that he had corresponded that had this in. So it was published in 1763. And it was entitled An Essay Toward Solving a Problem in the Doctrine of Chances. And I'll try my best here with early modern English. Given the number of times on which an unknown event has happened and failed, required, the chance that the probability of its happening in a single trial lies somewhere between any 2 degrees of probability that can be named. And that's kind of the money quote at the top. If there's a couple of links here, there's one from the Royal Society that shows the actual original letter. But then there's another one that's sort of written into contemporary English at UCLA Statistics Department has that version of it. So I've linked both of those. It's a pretty interesting read. Another mathematician, really famous mathematician named Laplace, picked up what Bayes was working on, and he added a little bit, but the results of that are now called Bayes' theorem. And it's used for a kind of inductive reasoning, as opposed to, say, deductive reasoning or ad hoc judgment or however. But there's a formula here, and, well, actually, before I draw it up on the whiteboard, the formula is probability of hypothesis H given data D equals the probability of data D given hypothesis H divided by the probability of the data times the probability of the hypothesis. And I've always found this to be confusing. But in short, it represents a credence. It represents a degree of belief in the probability of some hypothesis occurring given that we have evidence, that we have data that happened. And yet, even so, even though that really makes sense about how people make judgments, this area of statistics is not without controversy. Within the stats community, there's still an encounter, a big divide between the Bayesian people and the frequentist people. Okay, so let me break this down a bit. I had said that the formula has always been hard for me to keep in mind and understand, but the concept is not. Bayes' theorem lets us update the probability of hypothesis H in light of evidence in data D. And so I've drawn here that there's 3 segments of this. There's the first part, what we call the posterior. And that's the decision that you're trying to make now. That's what you're trying to arrive at. Okay, and that is a function of, it equals, the product of the evidence and the prior. So the evidence is basically conditioning the data. It's like what I had done back up there with those ratios. You want to take that data and make sure that it's not wildly skewed in certain conditions. So the posterior, probability of h given d, we want to calculate the probability that our hypothesis h is true given the evidence that we have in hand. And the evidence that we have is being represented by the likelihood, probability of obtaining the data if the hypothesis is true. And we divide that by the marginal probability of this data happening in any case, regardless of the hypothesis. That's called a normalizing constant. So you take the likelihood and you divide it by the normalizing constant, and that gives you something that it essentially represents, if you will, a coefficient for your evidence. And you take that and multiply it by what you knew before. What were you thinking? What was your judgment before you had this new piece of evidence? So you take the new evidence times the previous judgment, multiply them together, and you end up with your current judgment. Long and short. So let's show an example here. Foo Bartender, our sample startup, has been running a special on cookies and cream cocktails. I like those. There's a hamburger place near where we live, and we take the family there all the time. They have these. Anyway, Foo Bartender has been having some issues with quality assurance on those cookie and cream cocktails. It's basically a milkshake, really, with vodka poured in it. The problem is, given that we pulled a vanilla cookie from some bowl, and we've got a couple of bowls, we want to reverse engineer and find the probability that it came from either bowl. And so the thing there is we've got a little bit of Q&A, or sorry, a little bit of QA that we're doing here, because we've got bowls of vanilla cookies and bowls of chocolate cookies, and we have the idea that somebody's mixed them up a little bit. So we've got container bowl number 1 and bowl number 2, and those correspond to two different hypotheses, H1 and H2. First one, we've got a mix of vanilla and chocolate cookies in bowl number 1. The second one, we've got a different mix of vanilla and chocolate cookies in bowl number 2. Actually, it's even money on bowl number 2. There's equal amounts. But given that we pulled out a vanilla cookie, let's figure out which bowl we think it came from. What's the probability that it came from both those bowls? And this is really based on the cookie problem. One of the books that we'd recommended earlier on is called Think Bayes by Alan Downey, and a highly recommended book. So pulling a vanilla cookie out of a bowl is our observed data, D. And each of the bowls is going to be a hypothesis, H. The probability of D given H, that's our likelihood of pulling a vanilla cookie from each of the bowls. So now we can use Bayes' theorem to calculate the posterior probability, what we're trying to solve for, our judgment, probability of H given D for each one of those bowls, both of them. So there's some Python code that I'll show an example here, but to run it, you need to download part of the code from Alan Downey. And here's a link. It's on ThinkBayes, and the code module is thinkbayes.py. And just make sure that it's in the same local directory as you're working in for the other code that you have. Okay, I've got some Python here for doing the cookie problem based on the ThinkBayes examples. And so first thing here is I'm going to cut and paste this part. Okay, so it's pulling in ThinkBayes, and it's importing a class called PMF. So thinkbayes.py is that module from Alan Downey. And then one of the first things we do is we set hypothesis H1 and H2. Let me go through those steps. We set the priors. So the first step there is we create an object, PMF, and then we set the priors for it, respectively off of H1 and H2. The next thing we're going to do is update the likelihood. So that's the .multi function. We've got the likelihood that we're setting based on the mix of vanilla and chocolate cookies in the different two bowls. And then we go and apply the normalizing constant So we call normalize. And that comes back with its message. But what we want to calculate is the posteriors. So here, we'll just loop through this. For both hypotheses, H1 and H2, print out the bowl and print out the posterior probability. Blam. So we end up with hypothesis 1, the probability is 0.6, and hypothesis 2, the probability is 0.4. So that's probability if you have a vanilla cookie in hand as your evidence, which bowl did it come from? It sounds very simple, and I think conceptually it is. But you'd be amazed how complex this can get when people are making judgments. And you know, the thing is that here we have not so many variables to work with and not so many conditional probabilities. You can get into the situation where you have networks, and so Bayesian network, where you're looking at fairly complex relationships across a lot of different variables. But the nice thing about a Bayesian approach on this is that it's extremely easy to reverse engineer how it gets to the probability that it produces. It's extremely straightforward. There's no black box, per se. You can reverse engineer a decision and figure out why. Next, let's consider what we did before with ratios. Let's take a little bit more of a Bayesian approach toward that. Okay, so in this example, foodbartender.io has been gathering customer feedback about top bartenders. So, you know, we've got profiles of the different bartenders, and customers can come in and click for upvote or downvote. Popularity contest, but it gives us some really good feedback. The problem is that based on customer votes in the table below, which of the bartenders has a better score? So we've got the reigning champ, Deepali, who's had 45 upvotes over a period of time and 5 downvotes. But then we've got a new person on the team, Kirill, who has 2 upvotes, but no downvotes yet. If we were using a simple ratio, Kirill would appear to be the leader now because he got 100%. But really, that's probably not fair to Deepali. Okay, that's really a matter of making a judgment in isolation, because who knows, the next 10 votes that come in for Kirill could all be downvotes, in which case he wouldn't look so good. So, isolation in time. So instead, we're going to use a Bayesian approach here. We're going to take and apply a beta 1-1 distribution as a prior. Effectively, we're adding a coin flip to the scores. And so that is to say we add 1 upvote and 1 downvote to each of the bartenders and then calculate that. Again, that's applying something we typically call shrinkage. It's going to normalize the scores. So if we look at this, Deepali, a frequentist estimate would be 45 divided by 5 plus 45, so she could get a 90%. Whereas Kirill would have 2 divided by 0 plus 2 would have 100%. But from a Bayesian perspective, it would be 46 divided by 6 plus 46, again, adding an upvote and downvote to each. And that comes out with 88% for Deepali. And then for Kirill, we would have 3 divided by 1 plus 3 is 75%. So as you can see, Deepali comes out ahead, 88% versus Kirill's 75%. And that's really how things should be. Okay, in terms of computational thinking, data in the real world is almost constantly in flux. And that is in stark contrast to the frequentist notions of isolation. Bayesian approaches, on the other hand, incorporate notions of change, iteration on judgments, updates on the data, etc. So, going back to that statistical data modeling that I introduced earlier on, the frequentist notions of probability, bringing those into statistics, it really kind of fixates on outcomes. And it's not particularly good for taking into account that things change over time. In terms of computational thinking, there's an interesting lesson here for pattern generalization and abstraction. Recognize that many business use cases require solutions that adapt over time. They adapt to change, and the judgments must be refined over time. So Bayesian approaches allow for near-term decisions to be made while still incorporating the means to collect more evidence. That's your big data, by the way, and improve the judgments in the future. And that is how big data really changed this, because you can't, if you're streaming through petabytes of data, you can't just stop in isolation and make your judgment and then roll with it for the next 5 years, right? You have to go and update things over time because your market's always changing.